Okay, I think we can get started if you're all ready. Welcome everyone to today's Danish Sound Cluster webinar. The topic is intelligent microphones, and we have very expert guests here today. We have Eddie from his own consulting company, EBB Consult, and he works in a lot of different areas, and he's also involved with the EBU and the AES and audio forensics and broadcast. So he has a good overview of the whole industry and both on the product side and the production side. And then we have Keith. He's here from Wave Science Corporation, and he primarily works with audio processing and the cocktail party and separation of sources, and he's going to speak about that as well. And then we also have Stefan. He's here from Jabra, GN Audio, and he again has a very you're working with products and trends and technology, so he has a good overview of what's going on, and also has a background with microphones at Brolin Care before moving to Jabra. And finally, we have Brian Johansson from Grass, and he is primarily you're acoustical mechanical engineer and
Yeah,
working on the working with the hardware side of things. So thanks very much to all of you for being here. We're going to get started with a presentation from Eddie about microphones, where we're at now with the hardware, and then afterwards we'll hear from Keith. So take it away, Eddie. You can
thank
share your
you.
screen.
I will do that in a second. First, I want to show two masterpieces, Danish microphone, Danish designs. This is Rørbæk Madsen designed that for Bang & Olufsen, and it's still a popular microphone in many cases. And here's another one. It's a size like that. That's another brilliant design. It's small. It's got completely professional data. Also Danish design from DPA. So microphones are produced here, and I think the guys, Grass, B&K, and others will also say they are making good microphones. I will share my presentation. It should be right here. So, and I think I've got a split screen. I will just have the PC screen on here. And I guess that's... Do you see one or two screens?
We see two. We can see your slide and the next slide as well.
Yeah, okay. So I'll just see whether it, just share it one more time, see whether that changes it. Just a second. It worked a second ago. So
I forgot to mention, if anyone has any comments, you can write it in the chat. And if you have any questions, you can write in the Q&A chat, and we'll take the questions after each presentation.
excellent. Let's try again.
Yeah.
So share screen, and here we go. And like this. No, it's still two. You will have to see two screens here. Okay. Anyway.
Are you sure, Eddie, you can't just... Do you see where it says display settings up above your slide?
Display setting.
Is that a...
This is better, I guess.
That's
now it's one
perfect.
Screen.
Yeah.
Okay, great. Thank you.
Great.
Okay. It's all about microphones, whether they are intelligent or not. So I'm going to give a kind of basis, brush up on what is a microphone actually, before Keith comes up with all the intelligent stuff. About me, I've been somewhere before. I've been in the business for more than 50 years now, and in the right corner is the places where I roam these days, basically. This thing about microphones is actually very interesting. Also, if you're in the microphone business, because nobody throws old microphones away. They just want to store them and keep them. So it's a strange business. It has to be you have to trash it in one way or another to change it or throw it away. As long as it works, you're keeping the microphone, and still thousands of microphones are produced every day. What is it all about? It's the transducer, and it converts acoustical sound to electricity, basically, or into digital code. A microphone, basically, the first thing we talk about is a diaphragm. How does that connect with the sound field? That is most important thing. Then we can talk about the power plant that's behind it that creates the voltage or digital code or whatever is in the other end of attached to the diaphragm or membrane. So here is a diaphragm, and we can put some housing around it. That's nice. Then we have a pressure transducer. When we add some sound to it, then we will find out that we have an omnidirectional transducer or omnidirectional microphone, because it's a pressure it measures. Of course, it's a matter of having it as a small unit compared to the wavelengths we're working with, but then it will work as a pressure transducer. You could add some holes in this housing, and then you can have some inlet that will let some of the sound in from to the back of the diaphragm. And of course, you will have a kind of delay because it has another path around the microphone to get into the backside of the membrane. And then you have a gradient or a difference, and this gradient is what causes a pressure on or the movement of the diaphragm. And then you can achieve some other polar patterns, and by changing the hole in the back of the housing, basically you can make other polar patterns. This is a cardioid microphone, for instance, super cardioid, or in the end, when you have the same amount of admittance from the front and from the rear, you have a figure of 8 characteristic of this. These are all first order characteristics in the matter of the cosine function that goes into the description of this polar pattern. If you want to have some higher directivity of the microphone, you could design an interference tube. Still, you just have one diaphragm or membrane in the bottom of this tube, and what comes in on axis all is in phase at the microphone diaphragm. What comes in off axis will have different path length to the microphone, and by that some of the sound is cancelled in that way. So you have less vibration or pressure on the diaphragm in the bottom. If this should go all the way down to 20 hertz, it would be a very long tube. So normally you will make a kind of gradient microphone in the bottom on which you mount this interference tube to get some directivity at lower frequencies. At least it would have the same length as the boom pole, and that would be very unhandy. Another way to achieve directivity is basically the array building. You can form arrays and make beam forming by creating arrays. This is a simple version of that. It's a simple sum, but basically what goes on today is a lot of signal processing to figure out how to use the signals you get from the different elements of an array to make the kind of beam forming and whatever you will need for changing the directivity and getting more specific and higher directivities of microphones like that. So that is basically one way of or another way of doing it, of getting directivity, and now you have more than one element built into your microphone. And if we take all these groups, we look into the power plant, as I said, behind the diaphragm. You could have passive transducers, active transducers, and in the second row you can see names like dynamic microphone, AF condenser microphone, RF condenser microphone, carbon microphone, and in the end some MEMS digital microphones. What you may know is that when you have dynamic microphone, like a moving coil microphone, the voltage is proportional to the diaphragm velocity. If we talk the condenser microphones, the voltage output is proportional to the diaphragm amplitude. So that means you'll always have a 90-degree difference between dynamic microphones and condenser microphones. That's just one specific thing about the output of these microphones. We could take one sound source, a sound source. This is a person speaking, and that person has a language, okay. He will have some articulation, and there will be a speech rate, and he will have a speech level, and there will be some voice directivity, and in the end, these days, we also have experienced that there will be a mask put on that person. And the thing is, what can we do about this source to optimize what we get from him? If we talk about the language, can we do anything about it? Yeah, we can ask the person to speak another language perhaps, but also we know from news and film, we can make automatic dialogue replacement, for instance. So that's a possibility. What about articulation, speech rate, speech level, voice directivity? Basically, we cannot do much about it from the very beginning. The mask, okay, we can take that away, hopefully soon. Recording that sound source, then we have to consider different things. It could be a direct or diffuse field we are in. The direct field, we have only one direction of the sound. Diffuse field, we have all directions. And that really makes a difference to that microphone that picks up the thing. And the same dry reverberant, that's basically the same. We could have a source that's very silent, or we could have a loud source. So we have to consider how to get the right level. We could have one single source, but also we could have multiple sources. We might want to record multiple sources, or we might want only to record one single source among other sources. And we may have silence in the background, but we may also have noisy background. And of course, we have the weather, and we cannot do anything about that. But anything else here, direct diffuse sound, yeah, by processing the signal and looking into what the signal actually is like, we'll be able to improve these things by technologies. This is a sound field you may have seen or you have heard. These are two TV anchors as they sound like. And you could ask yourself if you ever would place a camera here, and you would say, no, you would not. But it's okay to place a microphone in that position on the chest of these persons here. Basically, when we have microphones, they can be the best in the world, but if we place them where the sound is bad or it is not optimal regarding the, for instance, intelligibility and things like that, we don't care. We put the microphone where we can put it, and that is sometimes a problem. Just to remind you that whenever we put microphones on the chest and head of a person, the spectrum will deviate in any position, and you have to take care of that. So if you are intelligent, you will take care of this, or you could have a microphone that already has a compensation for the positioning, or you could make a kind of active white noise, white light setting. So you could make a kind of equalization to a reference value. As you can see on the chest at 4 kilohertz, we'll lose around 10 decibels, and that means that we really lose intelligibility of that thing. The microphone itself, well, it's perfect when it's completely left alone. Anybody producing microphones, they take it to the anechoic chamber, and every disturbing object around the microphone is removed. And then we can have a perfect frequency response of that microphone. Probably will never use a microphone like that because in this case it could be a handheld microphone, so at least there will be a hand nearby the microphone. We may add a windscreen that may take off some frequencies. In broadcast, we may even add logos on the side of this windscreen. And again, we may add some COVID protection. So that microphone that in the beginning would have the most perfect frequency response in the world, after it has been brought to the field and used under the circumstances that we have to use it with there, then things has changed dramatically. Can we do anything about it? Yes, again, it's a question of processing the signal so we can get this white balance. Have we existing technologies we can use to obtain all these things? Yes, we have low latency AD solutions basically. We can build in processing. We have processing built in many places. For instance, for images in our mobile phones is no problem. We can make microphones arrayable, and we can build in self-correction. And we also have transmission technologies that we can use with it. So we can get the signal further transported to recording things or on air or wherever we want it. Can we do anything about this? Yes, it's all available in this case. And now we're talking about being mobile. As I said, the picture or image that we can make these days with our mobile devices is really amazing. We can get some sound, high resolution sound with our iPhone if we use a suitable converter for it and a decent microphone. Then we can add that to it, so at least we can process it in the post to the way we want to use the sound and shape it for our use. So for broadcast use, as one example here, what we could wish for here was some user recognition. Who is using this microphone? Then we could have some settings for that. There's no frequency correction. There may be a cutoff for low frequencies. There may be some correction for some windscreens or something like that. But basically, no correction regarding the position of the microphone and the sound source itself. There's no leveling built in, no noise reduction, no geotags on it, no metadata. That's basically all functionalities that would be nice to have in many situations, at least in broadcast. Other kind of use of microphones may have other wishes for what could be needed. Can we do anything about it? Yes, we can. So in the end here, I could say that at the EBU we had a session a couple of weeks ago, and it was named 4K in the Pocket, the sound crew in a truck. Basically, that's so easy to make pictures, a video now, and we can do it with our mobile devices, but the sound still lacks some technicalities. It's not easy. We have to really work with the sound to make it sound right. So what is intelligent microphone in this perspective? Well, an intelligent microphone could be one that is designed for a specific use. The microphone does not exist basically. It has to be designed for the use. That's one reason for having so many brands and makes and models of microphones. Intelligent microphone, well, it could be designed for automatic calibration or white balance, as we can do with a camera that automatic sets the white balance depending on the light, measuring the light, and then you have correction of the colors so you get your right white balance. Basically, you could do the same thing with the sound. And intelligent microphone, that is able to distinguish between and select specific sound sources. And that's where Keith comes in a second, talking about these possibilities. And then, of course, intelligent microphone could also be one that provided some metadata, so you could know what kind of data you got, what kind of microphone this would be. We already have a standard for digital microphones for studio use, the AES42 standard. It also has in the metadata, it will tell what kind of a brand and make model you're working with that can be transported with the data stream. And so these technologies, many of them are available. It's just a question of implementing them in this case. So thank you. I would invite you to check out the DPA Microphones Microphone University if you want to read anything more about microphones, get ideas about use of microphones. So by that, I will stop sharing here and back to you.
Thanks very much, Eddie. Is that free to access, the DPA Academy?
Yes.
Wonderful. Okay, we'll share that afterwards in the follow-up email. And also the AES42 standard.
Yeah, it's not free. Yes, if you're a member, it's free. You can get the standard. Yeah.
Great. Okay. We'll share a link to that as well.
Yeah.
If there aren't any questions from our audience or from our panel to Eddie, then we can move on to Keith. Is that all right? Yeah, cool. Keith, welcome again.
Thank you. So most people don't know me unless you're in the audio forensics area. I spend most of my time dealing with government people in different law enforcement agencies. My specialty, as Shelley mentioned, is the cocktail party, separating out one voice from another. So without further ado,
Excellent.
yep, can you see?
Mm-hmm.
I can't, hold on a second.
That's no good.
Technology is great when it works. Okay, I think I see what I'm doing wrong. And
Lovely.
are you seeing only one slide or both, or the look ahead?
It can just
It's
be
okay.
one. It looks good. Yeah.
Okay. All right. So, yes, Keith McElwain. My company is Wave Sciences. We're based in Charleston, South Carolina, on the east coast of the USA. Okay. So, Eddie's, I won't be able to add much to Eddie's nice presentation on microphones, but there's been a long history. The point that I would like to make is to play off a comment that Shelley made when we were preparing for this session about how it seemed that video was getting a lot of attention and had lots of new features, but audio didn't. And this has been a kind of pet peeve of mine, but it's just a reality, a fact of the industry, that technology goes in cycles. And back in the 60s and the 70s and the 80s, audio was the thing. I still remember hooking up my first set of stereo speakers and trying to make sure that I had them properly spaced apart and the cables correct, and that my loudspeakers were not canceling each other. I wanted the perfect stereophonic effect. That was a few years ago. But then, as I said, the technology cycles around, and GPS and digital cameras all of a sudden started getting much smaller and much cheaper and higher performance. And of course got combined in the smartphones, and then we got all the cellular telephone and cellular data. And so for the next 30 plus years, those technologies have been kind of in the forefront and getting a lot of the attention and investment dollars and everything else. So to further play off of Shelley's questions about the differences in, say, smartphone video, she mentioned she could take a video with her smartphone that looked great, but the audio was terrible. Well, one problem has to do with physics. The camera can see very far away. You know, I found this image on the internet of a smartphone hooked up to a telescope, astronomical telescope. So optically you can see to another galaxy, but the microphone's not going to reach that far. The wavelengths of light are much, much smaller. They travel without resistance from most media very far distances, like from other galaxies. Sound isn't that way. It has a very long wavelength, particularly in the speech frequencies compared to light.
Sorry, Keith.
Keith?
I think we have a
Yes.
problem with your slide. It's not changing. It's still the first slide.
Oh, that's interesting.
Mm-hmm.
Yeah.
I don't know why that is. It's still the first slide. Huh.
Yeah.
Let me stop the share and start it again and see what happens. Technology is great when it works.
Oh, excellent. So let's try. And if you change to another slide.
Say again. What are you seeing now?
We
That's
can
the
see the
second slide.
guy
Okay.
in the chair.
And now did it transition to the next slide?
No.
Okay, let me show a navigator. That is so strange.
Yeah.
Huh. Well, maybe I just won't be in presenter mode, and you'll just get my
That is fine
slide.
for me.
Does that look okay?
That's
Yeah,
fine.
you don't have too much on your slide, so it's still possible to see
Right. Yes.
everything.
Not a lot to read. I don't tend to like wordy slides, so
Appreciate
it
that.
that looks fine there.
Yeah,
Absolutely.
perfect.
Okay. So that was the previous. Then this is a slide where I was talking about seeing other galaxies.
Yes.
Is it showing up for you now?
Yeah,
Okay. All right.
perfect.
So moving on. Again, Shelley's question, why does smartphone video look great but sound terrible? Well, we see using reflected light for the most part. The sun shines, strikes an object, and then bounces back to our eyes. That's not how we hear. As in Eddie's presentation, the sound emanates from a source, and in the ideal world comes directly to our ears, right? But of course, we also get it by diffuse means, reflections. People like whales and bats and other creatures that use echolocation can locate and in a sense see with sound echolocation. There's a few people that are actually famous for riding bicycles around cities and making clicking noises with their tongue and being human echolocators. But that's not the same thing as hearing somebody's speech, right? So that's another advantage that video has over audio. And video has had automatic exposure control for a long time. And it's not that you can't get automatic exposure control or an audio level control or gain control, as Eddie pointed out in his presentation. But when you're an audio forensics guy, you don't like that because it interferes with so many of the nice noise reduction filters and the source separation things that games I play on the back end. We really frown upon the use of adaptive gain technologies. Now, one of the things that particularly somebody in forensics line of work appreciates, but also anyone in the hearing aid line of work, is the ability to focus on an object, or shall we say in the hearing world, a person's voice. Video is great about that. You know, I chose this image of a fence so you can see how you can focus in mid-range and kind of blur out objects before something that you want to focus on and beyond that object. The human brain can do that, of course, but we don't really have many audio technologies that can do that. As a matter of fact, we've had none until now, I'm glad to say. That's not the same thing as not being able to hear over there. We do have, as Eddie pointed out, microphone array beamformers and parabolic dishes, which both technologies take capture area from a wider, capture sound from a wider area and combine it in ways that tend to create a reinforced pickup pattern in the direction you want to hear, and tend to reject sounds that come from off axis. Now, that works great in some environments, like parks, or maybe when you just want to get the crowd noise, or this is American football, I apologize. But it's a classic example over here, because they use parabolic mics on the sporting field to hear the calls by the quarterback on the line, and to hear the collision of the shoulder pads and helmets to give a little color to the action. This is fine. I wouldn't necessarily recommend trying to use a parabolic dish for an audio forensics or surveillance operation. The other thing is that this referee in this image stepped over in front, right along the axis. Who are you going to hear the loudest? The quarterback in the far field, or the referee in the near field? Right. Same thing works on the other side of the quarterback. That crowd in the stands, they're going to be loud too. So one of the problems with directional listening is that you get everything along the line of listening, the axis that you're pointing at, and this can be a problem, right? It also can be a problem if you are ignoring something that you need to hear from the side. I went looking on the internet for the advertisement put out by a hearing aid company 10 plus 12 years ago, when microphone array beamforming first came out with hearing aids. And there was one hearing aid manufacturer that put out a person wearing a pair of horse blinders, right? To say that you don't want to just willy-nilly apply microphone array beamforming to every single audio product, because you don't know what you're missing at that point. People still want situational awareness. They don't want to be taken by surprise and startled because somebody's yelling fire and they're the one person who's not heading for the exit. Now, talked about video cameras shrinking, the GPS chipsets shrinking, the phones sometimes shrinking, sometimes getting bigger. I like them when they're small, but it seems everybody else is buying big, whopping big phones. But audio recorders are getting very tiny. Why not just use a lot of them, right? Well, with my area of interest where I am processing audio from multiple microphones, you have a problem of synchronization, right? You don't have the truck, right? That Eddie mentioned, where somebody's going to come and resynchronize the audio and do that real time. You want to make your recording so that all the microphone signals, all the channels are sampled simultaneously. And right now, that's a very hard thing to do very accurately. There's timing products out on the market. I think that's my next slide. Yeah, that can synchronize over Bluetooth down to video frame accuracy, but not down to a audio sample accuracy if you're talking about, particularly if you're talking about sampling at something like 48 kilohertz, right? But the industry, progress marches on, and we're getting better and better. You can buy a 32-bit floating point microphone with onboard digital storage that can probably take a week to fill up, and it has Bluetooth, and you can monitor real time. If it can keep a Bluetooth signal going and is the location. But you can live monitor remotely your 32-bit audio stream, which I love, right? If I could just get them to synchronize down to an audio sample basis. And there's Bluetooth synchronizers, wireless, for doing this type of thing down the video frame rates. Another advance lately that I think will keep going, particularly as Facebook and other people are dumping tons of money into augmented reality and virtual reality, is this 3D audio and putting sound in glasses and such as that, and being in the metaverse. This is a 19 microphone spherical ambisonic array recorder. It's about this big, about the size of 2 fists together, but it's quite good. It's made in Poland, I think. Company Zilia. I have no affiliation with them, but I have enjoyed giving a play. Nice compact form factor. You can hook it up with your laptop and get 19 channels. So I love microphone arrays. But 19 microphones is a lot of microphones. Quite frankly, I've experimented a lot with microphone arrays. I have a wearable vest with a flexible electronic microphone array on the front that's 64 microphones, and another one on the back that's another 64 microphones. So 128 microphones in a garment, in a smart garment. I've worked on systems, custom systems for governments that went up to over 1,000 microphones. Right, that's a lot of microphones. And it's a lot of microphones to do something that human beings do with the biological equivalent of 2, right? So Facebook and Microsoft and Amazon and all these companies are throwing tons of money into artificial intelligence and neural networks, trying to figure out how to teach a computer to hear like a human being, right? To get 1,000 microphones down to 2, right? And it's more than just mics. You've got this nice acoustic baffle there that creates acoustic shadows for sounds arriving at one ear and the other ear is shadowed. And you have a supercomputer. Not all of ours use its full capacity. All of us use our full capacity, but it's there. And it's constantly working, making sense of your audio streams. This has been something that people have been researching for a long time, since right before I was born. Colin Cherry, back in 1957, dubbed this ability of human beings to hear in a cocktail party environment the cocktail party effect, right? And the cocktail party problem of why we can't do it, right? why we haven't been able to construct a machine before now that can actually take two microphones and separate out voices that are speaking simultaneously. Now, I would normally like to play this little very short cartoon, but it's back from when I was a kid. It is character Foghorn Leghorn is dating the widow hen and ends up having to take care of Egghead. I like Egghead. They play a game of hide and seek. Foghorn goes and hides in the wood bin. Egghead can't find him, pulls out a piece of paper, scribbles some math, picks up a shovel, goes digs under a tree, and up pops Foghorn. And he says, you know, how did this happen? How did this happen? And Egghead scribbles out, shows him the math he scribbled out. So it's all in the math, right? He moved Foghorn from the wood bin to out buried underneath the apple tree, right, with math. And I like that analogy because that's what we do. One of our acoustic engineers, somebody said, we've got to repair your computer. Can you get, or can you come to work, or you need to take some time off while your computer's under repair? And it says, computer, I don't need a computer. I have pencil and paper, right? We have worked with the acoustic wave equation. I won't go into that, and partial differential equations in the time provided. But we worked out from the acoustic wave equation for wave guides. These rooms that we're sitting in can be treated as a wave guide. And we came to some realizations that allow us to do something very novel. We are now able, with as few as 2 microphones, to mimic what human hearing does in separating out, focusing on an individual sound source, specifically a point source, right? Our command of the math isn't able to do it for diffuse sources, but your mouth is small enough that it's a point source, right? And it works very well. We can replicate binaural hearing. We've used like Sennheiser binaural headsets and made recordings, and we can not only separate out multiple speakers in a room, we can jump over, like human hearing can, ignore or reduce a speaker in front to hear the speaker on the other side, right, further away at the other end of the table. And just like human hearing in the cocktail party, you can select who you want to listen to. And we do it for forensics, right? You've got a human in the loop that has to click and drag like you're in your digital audio workstation and say, that's the voice that I want, right? But using this math, which we have a very strong hunch supported by circumstantial evidence, is probably the same math that's going on inside the human head, we figured it out. So I'll close by saying, it's very similar to Eddie's comments. There's a lot of things that can be done with microphones. Lots of the bits and pieces are there. You can find different combinations of these things in different products. And we're not that far from getting to a time where we can move enough intelligence out into the microphone that we can maybe even skip just being straight intelligent microphone and go all the way to artificial intelligent microphone. Sorry for the buzzword. Everybody wants to talk about AI. I'm more of a ML guy, machine learning guy, but we're getting very close to, regardless of which term you like to use. That's it.
Thank you very much, Keith. Let me just change the view here. Hello, everyone. I've muted you all, so you can unmute your microphones if you need to speak. Thank you very much, Keith, for sharing that about the history and the status, and of course your own solution as well. Okay, perhaps we could start with I already want to ask you more about your 128 microphone smart garment. Is that a wireless?
Yes, actually. Yeah, you can listen by Bluetooth audio. Yeah.
And it's synced.
Yes.
Okay.
Yeah. You steer it by just where you turn your torso. Right.
Okay.
So you just square up to whoever you're listening to, and they come in loud and clear. If you Google my name and TEDx, you'll find a talk that I did about that technology.
Excellent. We can share that as well. Yeah, for sure. So, Brian, I was going to ask you about the kind of status of how it is in the measurement microphone world. Now that you work at Grass and previously at B&K, I know it's a completely different application, but perhaps you could shed some light on is there even a demand for metadata and additional technology?
Sure. I think so. Like we're also taking small steps in that direction. And actually, we just launched like 2 months ago an intelligent microphone. You can say, with if we want to process a signal, then of course we need to pick it up by microphone. And then to make the processing more robust, then we want the microphone signal to be the most reliable as it can get. In daily use, we calibrate with a known sound source in order to learn the microphone sensitivity, making sure that the channel gain is set correctly. Then this calibration can be time consuming all by itself. And it frequently involves opening or disassembling, like the test fixtures to reach the microphone. And then great care has to be taken when dismounting the fixture. Sometimes we don't even have the physical access to the microphone, which excludes any calibration. And there could be an unreachable hidden surveillance microphone, for example. And we thought about how it could be easy to verify the sensitivity, that the sensitivity was within expectations. So we placed a microprocessor out in the preamplifier to generate a signal out there, just next to the microphone. And then by use of this second signal generator, we can apply a waveform directly to the diaphragm, and then the diaphragm will turn a response, and then that will be measured and a verdict will be made to ensure that it's still within tolerances. So to make a verification of this unreachable microphone. And then we know that the microphones also have environmental parameters have influence on the microphone properties. Typically, a microphone has a temperature coefficient to be accounted for. So we also embedded an environmental sensor to acquire temperature, humidity, and static pressure. And these parameters can be retrieved by request. And then, while this is not a calibration tool, it can still function as a predictor how far the sensitivity lies from expected sensitivity. And this information can also be fed to the DSP for flagging the degree of measurement quality and to change algorithm accordingly. So you know some of the parameters, like the temperature, because you have to account for this temperature coefficient.
And humidity as well?
And humidity as well, yeah. And barometric pressure. So that's a small step to going in to have a clean signal you pick up to process furthermore. So we put actually some intelligence in near the microphone, and I think we'll see more of that.
Yeah, you're mostly concerned with ensuring that your calibration and measurement is still as accurate as possible.
Yeah.
Under all circumstances.
So we can apply these normally algorithm we use, and they still will be valid.
Yeah, and also remotely, I guess, if you're
Mm.
measuring some
Yeah,
kind of industrial machinery or cars
yeah,
and
exactly. Production test or
in all
whatever.
different environments.
Yeah.
Yeah. Okay. Thanks a lot for sharing that. And Stefan.
Yeah, I can actually also say that is also count for our world, even though that we are not using high-end microphones, but we are using a lot of directionality in our products to focusing on where the voice is coming from, compensating from the length of the boom arm and where the microphones are placed to pick up the sound best possible in any kind of environment. So we are actually also calibrating our systems and also to get the directionality to work as best as possible, both from mechanics as well as before we are edge processing it and try to filter out unwanted noise and voice in the environment. So that is, you can say, part of our daily task when we do designs of our products. We also work with the metadata actually. We also close collaboration, for example, with Zoom and Microsoft Teams. And they're actually requiring, as a part of their new standards that we are certifying up against, that you're delivering a metadata layer. So one thing is the audio quality, and also if it's a wireless product, then the wireless link quality, these type of parameters, so they can try to identify that you have the best possible collaboration. And for those of you out there, we do, you can say, collaboration devices. We are headsets, speaker phones, and cameras, and these type of things. And we work, you can say, in a limited frequency range so far. So even though that the great guys presenting here shows how you do it for recording music, broadcasting, and all that, we are still in the space we call wideband up to 7.4 kilohertz. This is the frequency range that we work within so far. But of course, with the new type of immersive experiences, we actually also try to go beyond that frequency range. So we are hitting, you can say, all the same dilemmas. And it was also very interesting to hear Keith talk about how you reproduce the ears of a human being. You probably also know that we have these small earbuds you plug in. When you plug in small earbuds, you're actually destroying that system mechanically around your ears and how you are capable of locating where sound is coming from. So with our, you can say, hear-through functionality, that's you can say a safety measure that you can both listen to music or be on conversation and hear what goes on around you. You will probably, if you test a number of our products as well as our colleagues in the business, that not all of them are very good of reproducing where the sound is actually coming from. Yes, you can hear what's going on around you, but the spatialization is not in place yet. And that is, you can say, a new area to crack on figuring out when you then block your ears, how do you then reproduce in the product and embed it in the front end, how the directionality works. And that is also a little bit individual, so that's also personalization built into that. And if you then on top of that also try to compensate for the hearing ability, then you have quite a large equation you try to cover.
Okay. I didn't think about it before with the hear through mode, but the microphones are on the back of the earbud themselves. So the distance between the eardrum and the earbud is what's causing this error.
Yes,
basically.
and you can say the reflection from your ears is not working anymore because best case you will have a microphone at your eardrum and have your mechanical, physical, acoustical system around that, and that will give you the natural directionality. But with headphones like you have on or small earbuds, then this system is gone, and you need to reproduce that.
Yeah, I see. Okay. Did anyone else have any comments to
I think that
Stefan?
one thing, and that is the speech level, your own speech level, especially these days where everybody is having a meeting on their computer, and they will disturb each other in the open plan offices. I think the feature of having your own voice presented in your earbuds or a headphone is very important, because then you lower your voice, the louder you can, the more you can hear yourself, and that helps keeping the noise level down in the office environment. So that's an important feature of adding those microphones there.
And in our world of communication headsets, that's what we call the side tone level, actually coming from the old phone that you can hear your own voice, so you balance your own output from your mouth. Not everybody is aware of it, and probably all of us have sit in an open office environment where some of your colleagues are very loud when they put on headsets, and other people try to be more quiet. But that is actually, you can say, the capability of hear your own voice and balancing it when you are communicating, because the microphone and technology do not need you to speak loud. It's something happening, you can say, in your head, that you feel that you need to be louder to be heard more clear.
Yeah, and it's a great feature that you have in the app. I just noticed this a couple of weeks ago, that in the app you can set the side tone level yourself, so you can, yeah, find a level that's not too distracting. So you're not hearing an echo, but yeah, you don't feel the need to speak loudly all the time. That's great. What else do we have on
I
our
would like
list here?
to ask Keith a question. What's the bandwidth of your system, the frequency range?
There really isn't a limit. We haven't done ultrasonic testing, but we've tested all the speech frequencies and higher. It's just a question of what audio you feed it.
Okay.
There's several aspects going on. Localizing, even the human hearing system kind of splits localization between low frequencies and high frequencies. So there is part of our method involves mimicking what the human brain is doing. So if you cut out too many frequencies, get too band limited, it may make it a little fiddly to adjust to find the right person. But it's the same way with human hearing. If you've lost your high frequencies, or in some strange situations lost your low frequencies, it can also interfere with this cocktail party effect. So it's quite expected that that's going to happen. But the math itself doesn't care, right? But the ability to mimic human hearing may be affected if you drop out too much of the normal speech frequencies. Hopefully that was not too down the rabbit hole.
Excellent.
Keith, I read something about visible light communication. Is that something that's relevant? Perhaps you could share a little bit about that here, or is it not relevant for this audience?
I think it's relevant from the standpoint that it's another hearing and noise technology. One of the aspects of the modern world is, I made a derogatory reference to Bluetooth earlier, because I frequently lose my Bluetooth link when I'm out in very busy, crowded spaces. The RF spectrum is getting very crowded. But it also, having come from the surveillance and forensics area, I am also a big privacy advocate, right? And RF data tends to go through walls and such as that. So I appreciate the ability to send sound by light, because it's much more privacy enhancing and much more reliable. Right, so scattered around the office, we have some of these audio light bulbs. We put a microphone in the base, and you screw the light bulb in. When you flip the light switch on, you have power to the bulb, therefore power to the microphone and the transmitter, and you are broadcasting audio. I have a patent or two on the idea of integrating that into as a replacement back in the day for these systems for short range hearing impaired headsets in like churches and museums and such, where you would just put light bulbs over the altar, over the choir, over the lectern, or over a painting, right? And the person could switch on their headset and have a little photo detector, and it would convert it back to sound. So you end up with something that's a little more local, a little more broadcast nature. Bluetooth doesn't like to broadcast. It wants to be point to point and source to destination, and only one way. So there's a lot of kind of interesting little advantages to it.
I fully agree with you, Keith. Also concerning the privacy, and that is, you can say when you run radio signals, they can travel quite far, and of course security is a high concern. Regarding broadcasting and Bluetooth, actually with the latest Bluetooth LE standards coming out, then you will be capable of doing actually broadcasting to overcome the use case you just described here. So that will be, you can say, natural for hearing aid users and potentially headset users in the future, that you can be in areas where there will be broadcasting available that you can move on to if you like.
So what I'm hearing is there is a lot of new technology being integrated in each of the different markets and sectors, but there's never really going to be one particular standard for metadata, perhaps, or it will just depend on the user case. I know that Eddie is involved in creating some standards, and I don't know if you have anything to say on that, Eddie. Of course, there are standards such as like in Bluetooth or the AES-1, but there's never going to be a specific standard for metadata, for example.
Basically, the AES-42 already contains some, as I said, some kind of metadata, because it is signaling what kind of microphone you have, what is the gain setting, and whatever kind of technical information is brought along with the signal. So it's kind of already there. But there are so many other areas where you could use these metadata. Of course, the recording device or transmission device, if it's a mobile phone, has some of these features, so you could add them to the sound, get them from your mobile device, for instance, for a start at least. But as I think Morten mentioned at a point in time, you have a fingerprint reader on your mobile device. Why don't you have that on your microphone? So the microphone will know who's actually using this microphone, and allow you to transmit for one thing, and knowing who is that, what is the setting, what would the level setting be, what could we do to enhance intelligibility. Whenever we are in the studio, we will use compressors, for instance, and we will look into the to intelligibility in one way or another. Why couldn't we do that already in the microphone? So we have almost a finished product when it leaves the microphone, with all the data information we need about it. These days we have digital wireless systems that also transmit some kind of metadata. For instance, the battery level of your transmitter. It's good to know when the battery is running out, and this kind of data is already there. So there's a wide area of possibilities that you can add to this. Further, we move on to 5G technologies, and you could say that 5G has perhaps a limited reach, limited range, but within short distance, you have the possibilities within from sending to receiving point. You could transmit all the data you would need for the purpose. And that's a whole other story about what kind of frequency ranges that will be available for us, both in professional but also in more domestic use of wireless systems in one way or another. That's another discussion, and it seems like the audio guys are the losers, big losers, because if we get less frequency ranges available to us in this case. So we also have to be smart regarding that, how to use that still more limited space for the number of channels that we actually need for the standard productions that we are working with. So there's a lot of things to look into on this. Unfortunately, so far it's being digital is not always the best solution, because anything digital takes time to convert, and especially if you package, you have bit reduction or anything, special codecs, it takes time to pack it down and to unpack it again. That takes time. We know from in-ear monitoring, for instance, if you have a digital system, some singers are not able to sing with in-ear monitoring system where their own signal have been transmitted by a digital wireless system. So we still have problems with that. And if you're synchronizing bigger systems, you may have even more latency in your systems. So that's something else we have to deal with, that actually looks more difficult compared to the thing of adding some simple basic processing of the audio signal, which seems to could be made more easy compared to the other problems we have in that sense.
And I think I can echo that, because we also have, you can say, each time we add edge processing, then we add latency into the entire audio pipeline. And we also need to comply with a number of standards to be Zoom compliant or Microsoft Teams and all the others. And they are quite strict because they also need to be synchronized with the video. And so it's we also try to say, okay, how can we take great new algorithms that can do fantastic stuff that has been trained on huge data set and then compress them into very, very small, low latency networks that can run in a battery powered device. That is also what you could say a lot of time is spent in our audio research, try to come from the big computers and neural networks there to very, very small battery powered solution. And that is both counting for our headsets as well as in our hearing aid part of our company.
Thank you very much, everyone. We think we have a question here. Sorry, I didn't see it from earlier. This is from Nagendra. I believe it's for Eddie. Unidirectional versus bidirectional. Which microphone is better for digital stethoscope? Anyone in our panel, you're welcome to answer this.
That should be the pressure microphone, the omnidirectional microphone, I would guess, for that purpose. Because if you use a stethoscope, there's no directionality. You don't need that. You need a pressure, and especially depending what the purpose is. If you need low frequencies, the pressure microphone goes all the way down to DC. You actually have to drill a hole into the system to avoid it goes down to DC. And the bidirectional, you also have the problem about each side of the figure 8, they are out of phase. It's a positive one side and negative on the other side, and that may end up with some confusion in that. So I would say the Omni microphone or the pressure microphone, closed box microphone, is the one that would work in that case. So it could be just like this one here.
I think you've done that before
I will
already.
share.
Go ahead.
I can share very quickly that I did some experiments with Hydrophone as a stethoscope. Since the body is primarily water, you have an impedance mismatch when you come from this hard metal plate and stethoscope. So I took a hydrogel and put it in a Ziploc bag and put a hydrophone like we use for our sonar work, and it worked fantastically well. You could just kind of lay it on the chest, and we ran some like Wignerville, high resolution spectrograms, and the resolution was amazing and the sensitivity was amazing. But it was an interesting lab experiment, and maybe not ever a product that comes out of that, but it's a little maybe out of the box thinking about using different types of microphones
about
in non-standard ways. Yeah, exactly.
Yeah. Okay, I thought you made people swallow the microphone, the hydrophone.
There is actually a bone mic out there, microphone that attaches to the teeth. So you wear it, it's almost like a partial mouth protector, mouth guard, and the military guys wear it so they can communicate when they are diving or jumping from airplanes, very loud noise environments. So the microphone is actually resonant right inside the back molar toward the palate.
Wow.
Very well.
Some real James Bond stuff there. So how do they speak when they're underwater, when they're diving?
So they've got, the full face mask, rebreather type of apparatus, right? So there is air there, not just in the mouth apparatus, breathing apparatus.
Excellent.
Yeah. I can also add that now you're mentioning this case that some of our latest true wireless products actually have VPUs inside that are listening inside the ear canal to overcome if you are in super high noisy environment, then you're still able to communicate because we are picking up your voice not from the sound coming out of your mouth, but actually what travels through your head instead. So these are, you would say, technologies to try to improve difficult situations.
Okay, that's a microphone that's pointing in.
Yes, and picking up voice in there, and that is also used by military and others, and now it's also available in, you can say, consumer products.
So maybe Eddie needs to redo his paper about the equalization of the microphone locations to include the mouth and the ear canal.
I'll do that. The in-ear equalization, yeah.
Okay, so I think we've covered a lot of different topics here so far. The latency, the importance of synchronizing, of course, metadata, some of the standards that we'll share as well, and some interesting new emerging sensors and applications for those from Keith. So if anyone is interested in hearing more about his wacky inventions, we will share his contact information as well. If there aren't, one moment, there's a question here. Wind noise. Are there any interesting ways that can be approached on reducing or removing this issue with mic diaphragms, DSP techniques, or anything else? That's from Kirtan. And I suppose relevant for most of you in various
I guess
environments.
it's relevant for everybody. And,
Yeah.
there's put a lot of effort into that from those making the mobile devices because it's out in the wind. And basically, you can see some algorithm that can do really nice job. And you see for post-processing, like isotopes, D-wind algorithm and things like that are quite efficient. The problem is still how to deal with that real time because it's so low frequent and it's almost DC, and how to cope with the DC that's ongoing for seconds and remove that. Of course, you make high pass filtering basically to avoid most of it when you are outdoors, but still you may need to get in an environment represented on your phone or your microphone, and you may want to have low frequency components, just getting rid of the wind. but basically you may exaggerate your input because the movement you add to the membrane of the diaphragm is much higher. The amplitude is much higher compared to what the sound waves is actually doing. So you really also have to see to think how you control your diaphragm in that sense. And again, the omnidirectional pressure microphone, then you have a diaphragm in front of a closed chamber, and that will keep your diaphragm in position. If you have a pressure gradient, you have air on both sides, so it can move dramatically. So whenever you have a gradient microphone, a pure gradient microphone, you will have at least 10 dB or more, 15 dB more of wind noise in that microphone. So if you want to do anything to control it, you should start out with pressure units, and you may use more microphones for controlling it better.
Yeah,
Eddie,
I will also sorry. Okay, so I think it's a classic DSP discipline in headset environment, because they are in many areas exposed to wind noise. One thing is what you can filter out DSP wise and try, but I will say that the mechanical construction is equally important. We have a wind tunnel in our research lab where we run our headset through to ensure and understand both the mechanical as well, because everything you can move mechanical, then you can reduce the amount of DSP afterwards. So design is super important around the microphone.
How about the microphone releases by various manufacturers in the last year? They started increasing the AOP, the acoustic overload point. Some of the distortion from wind noise, of course, is related to the diaphragm moving too far. I'm wondering if that's going to help make wind noise less of a factor going forward. I'm hopeful.
Yeah, I don't know any of these experiments. I know what it looks like when the membrane gets exaggerated, and where the noise shows up because it's a high frequency noise. Basically, you have first a low frequency component, and then the distortion components, they grow up, and you can control them to some degree, but still I don't know whether you can have a specific construction that better deals with the distortion components that occur.
Let's ask Brian. I was thinking this is maybe relevant for grass. I know you're doing some things to prevent the mechanical, to reduce it mechanically, but are you also using DSP to reduce wind noise?
No, we only consider the mechanics in a microphone. The DSP must be done by someone else. But we use some kind of grid sometimes, or also just foam around, because we know that work. And so there's also sometimes we look at new materials to do that elimination, but it's simply mechanic what we implement.
Mm-hmm. And no automatic sort of switching of the microphone amp. There's nothing smart happening in there. If, for example, there's a lot of wind noise, that it would have a different, filter it automatically, or
no, not in this regard.
No, not yet.
Not yet.
Okay, great. Let's move on to the next question, unless anyone has anything else to add about wind noise. Okay, from Shin Hui, can a microphone inside the mouth and ear canal generate intelligible speech? What may be lost in speech? Maybe Keith?
I think you can get some, there's a few YouTube videos for this company that makes this canal mic. a molar mic, I think they call it. If you just go into like YouTube and type molar, like your tooth, type mic, you'll probably be able to find it. The company's name slips my mind at the moment. They're based up near Fort Bragg in North Carolina, USA.
I'll try and find the videos and we can share it afterwards. But I suppose the quality isn't amazing, but let's find out.
It's understandable. It's intelligible. You're not. I wouldn't use it for broadcast, except in certain circumstances where you want that kind of feel to the audio.
When you want that kind of feel, like
reality TV. Yeah.
Yeah. Okay. I was remembering some. Is it the Red Hot Chili Peppers or where he like I don't know swallows the microphone? Who is that? Yeah. It didn't sound amazing. Okay, great. That's all the questions we have for now. Yeah, I think if no one has anything else they would like to add to the discussion, then we could wrap it up for today. Thank you very much, Eddie, for your presentation, and for your presentation, Keith, and to Stefan and Brian for being part of the discussion as well. For any of those Danish producers of Danish microphones or out there, we hope this was inspiring for you. And please, if you have any feedback, you're welcome to get in touch with us. And we'll also share the contact information of our panelists today, alongside some links and the presentations and things. So yeah, thank you for being here, everyone. Please take a moment to fill out the questionnaire. That helps us to improve the events we're doing in the future. If you have ideas for other topics, we're open to those. And we do have a webinar in the pipeline about emerging sensor technologies, which will also include a bit more machine learning and /AI/ deep learning as well. Okay, great. Thanks everyone for joining today.
Thank you.
Thanks.
Thank
Bye,
you.
guys.
Bye-bye.
Bye.
Bye.